Okay, this video is all things with bivariate data. So again, if we take a look at the back matter of the book, all of these Tech Corner references, they tell you the page in the book. They go from 1 to 32. We don't need that many. Obviously, we didn't make it that far just yet. But from 1 to 32, those all correspond through sampling if you go to student resources and look at the TI-84 Tech Corner. So these are the 1 to 32. So anything not covered in our little calculator video series can be found there. So for all things regression, I wanted to take a look at a problem, an example really in 3.2, because it works the entire way through, so you can see all the pictures in the book if you want to flip, and more importantly, computer output. And so pause the video and enter the values here for miles driven, one long list there, and then prices as well. And then we will work through you can see here, we'll do the scatter plot, we'll get the regression line and everything else that we need. Okay, so now that we're ready, all the data I have entered into list 1 and 2. So list 1, my miles driven is my explanatory variable, and based on the mileage, this is the price that was recorded whenever these vehicles were sold. And again, the expectation for a negative association. So as my explanatory variable is increasing, the more miles there are in the vehicle, my response is decreasing. And again, it is also explanatory, and we think about which one is being used to predict the other one. And so we're trying to, our regression line is a model to predict the price based on the miles driven. And so that's another just clue, I guess, if you think of it that way, that that's our explanatory variable. So under stat, I can calculate now my least squares regression line. Why they don't call it the least squares regression line on the calculator, I don't know, because there are other models that would be linear regression, but it is either 4 or 8. I lean towards 8, and you can see the difference between the two of them. 4 is AX plus B, which is more of an algebra base, and then number 8, the lin reg with A plus BX. Better matches the textbook, and better matches the computer output we see when we're looking at statistical output, which we'll also get to with this problem as well. So if we go to number 8, it asks for list 1 and list 2. And if we go down to store regression equation, this is so that if we wanted to put it directly into y equals, just to preserve those decimal points, the shortcut is alpha trace. And that brings up all the y vars. So this is just telling me it's going to store it into y1 for me. And if I calculate, I have my slope and, or I'm sorry, intercept and slope here. So the price, the intercept with 0 miles somehow would be $38,000. And then how much it's predicted to decrease, because again, my regression line is just a prediction for it, for each mile that is on the truck. So what is missing here is my R and my R squared. If I go to mode, if that happened to you as well, you should be able to go down to your stat diagnostic and turn that on. If you have an older calculator and you don't have the option that looks like this under your mode, then it is just a matter of going into the catalog. So second 0, and that will take you to the diagnostic on. You can just scroll through for that. So if I hit enter again, second enter, just to call it up instead of going through the menu, R squared is that coefficient of determination. And so the proportion of the variation that we see in the sale price, so the proportion of variation in Y that's explained by this regression model using the mileage to predict that sale price. And then my correlation coefficient R is negative, which should always match the slope. And that's telling me that I have a pretty moderate to strong negative linear relationship there. So if I go to my y equals, second y equals, to graph this, my scatter plot, again, asking me for list 1 and list 2. I'm just going to use zoom 9 to take a good look at it. And so that is my scatter plot. The regression line, again, was stored into y1. All of that was taken care of for me. If I go to my y equals then, I'm going to turn this off because one of the other graphs that we needed to take a look at was the residual plot. This is assessing whether or not the model is appropriate for use. So if the linear model is appropriate or not. So we had a moderate to strong negative correlation. There didn't appear to be any other kind of shape to the points. Sometimes it's so subtle though that the residual plot is just a way to zoom in on what is happening. And so if I go down to my Y list instead, the calculator automatically, it didn't tell you, but it automatically created the list of residuals for you whenever you ran linear regression. Otherwise, residuals are calculated by taking actual minus predicted. And so if I was curious, say the mileage on the truck was maybe 35,000 miles. If I entered 35,000 into my regression equation, figured out what the cost was predicted to be based on that model, and then took what it actually was at 35,000, which I'd have to be given, and subtract, that tells me what my residual is. So if you go to second stat, that is your list of lists, and that resid list should be there. Now, it is always from the last regression that you ran, so you have to work through linreg. So if I enter that and then hit zoom 9 again, I should have a pretty nice balance of positive and negative residuals. Now, on the other video with univariate data, we looked at the normal probability plot where we wanted to see a linear relationship. That gets confused an awful lot with my residual plot. And I think because they're both ways of just assessing. So the normal probability plot was to assess if the data was approximately normally distributed. The residual plot here is to assess the appropriateness of a linear model. This we want to be a hot mess. This is completely scattered. We see no pattern whatsoever. The residuals appear to have the same magnitude, positive and negative. Be careful. Whenever we worked through this, some people said that it was even, and that's not what is happening here. So just this random scatter instead is what I'm hoping to see whenever I work through these. So to get back to my equation, because I want to compare it to the output. So again, the output always being so important and something that you're more likely to see on a test than keying in a bunch of data yourself. So my slope and my intercept first and then my slope, that follows in the book as well. My R squared will be on the computer output. My R will not, but it's easy enough to find. So if we go back to the pages in the book, and this is quite a bit farther down, interpreting my computer output. Here I have, if I can zoom in a little bit, my mini tab and jump output. So just looking on the left-hand side of the screen, that same y-intercept, that same slope that was there. And then my R squared of 66.4. On the calculator, it's a proportion, so it's 0.664. Whenever you interpret it, it is the fraction or percent of variation. So it's just a formatting of the numbers. The extra piece I see here is my standard deviation of the residual. So on average, how far do my points vary from the line? That's what the residual is. It's the distance I see from the actual point and what would be predicted for that. So the smaller the standard deviation, the closer the data points should fall to that regression model. R is not given on here anywhere. You can easily find it. It is the square root of r squared. So this again, though, convert to a decimal point, make it 0.664, and then pay attention to the sign of the slope. Because if you have a negative slope, you're going to have a negative correlation coefficient. So the jump is a little different. The r square is there, so that should be super obvious. But the standard deviation of residuals, instead of being called S, it's only labeled as the root mean square error that's there. Otherwise, the intercept again shows up first and then the slope. So all the more reason to get used to that A plus BX notation, where A coming first represents the y-intercept and then B represents the slope. The other values that are listed on the input would be useful for chapter 12 whenever we do our test of the slope. And so we would use the second line. So if you look at the miles driven line in either output, the standard error that's listed there, the 0.03096, we would need the T column, or T ratio is the test statistic. And it's a T value whenever we're working with slope and analyzing it. And then the P value is the last column. So we would use that miles driven row in its entirety whenever we do inference procedures for slope. So the test or the confidence interval. So again, all things bivariate data. It doesn't seem like an awful lot, but again, more along the lines of making sure everything shows up in your calculator like it should. So you're getting the r squared and the r, you understand the residual list is created, and perhaps more importantly, recognizing how all of this maps onto the computer output, which if you're looking in the hard copy book, is on page 129.